Hi, this is Josh from Over the Shoulder Coding, and today we're working on day 7 of the Advent of Code 2018 challenge. Day 7, the sum of its parts. You find yourself standing on a snow-covered coastline. Apparently, you landed a little off course. The region is too hilly to see the North Pole from here, but you do spot some elves that seem to be trying to unpack something that was washed ashore. It's quite cold out, so you decide to risk creating a paradox by asking them for directions. Oh, are you the search party? Somehow, you can understand whatever elves from the year 1018 speak. You assume it's ancient Nordic Elvic. Ancient Nordic Elvish. Could the device on your wrist also be a translator? Those clothes don't look very warm. Take this. They hand you a heavy coat. We do need to find our way back to the North Pole, but we have higher priorities at the moment. You see, believe it or not, this box contains something that will solve all of Santa's transportation problems. At least, that's what it looks like from the pictures and the instructions. It doesn't seem like they can. Sleigh kit, some assembly required. Sleigh? What a wonderful name! You must help us assemble this sleigh at once. They start excitedly pulling more parts out of the box. The instructions specify a series of steps and requirements about which steps must be finished before others can begin, your puzzle input. Each step is designated by a single letter. For example, suppose you have the following instructions. These instructions here, visually these requirements look like this. Your first goal is to determine the order in which the steps should be completed. If more than one step is ready, choose the step in which is first alphabetically. In this example, the steps would be completed as follows. Only C is available, so it is done first. Next, both A and F are available. A is first alphabetically, so it is done next. Then, even though F was available earlier, steps B and D are also now available. B is first alphabetically of the three. After that, only D and F are available. E is not available because only some of its prerequisites are complete. Therefore, D is next. F is the only choice, so it is done next. Finally, E is completed. So in this example, the correct order is C, A, B, D, F, E. In what order should the steps in your instructions be completed? To begin, get your puzzle input. So we have a lot of puzzle input, but it would be much easier if we just steal this for 1 second and work with that first. So what are we going to do? This seems like a directed graph problem or a breadth first search variant. So we could have a set of possible nodes to work on. Starts with C, and then pick the first alphabetical node and remove it and its edges. So first, before that, we'd even need to construct graph of nodes and edges. Read nodes and edges from input with regex. Okay, so we're going to need regex, and let's read our input file. So we're going to make our graph of nodes and edges. And the graph is going to be So our graph is going to be a dictionary of the string key, so C over here, and then a set of nodes that C points to. So we're going to do pattern. Instead of C, we're going to have a letter. Instead of A, we're going to have another letter. So for line in lines, so let's see if we can search correctly. We get C, A, C, F, A, B, A, D, B, E, D, E, and F, E. So that looks good. Let's put that into a dictionary. So let's also import default dict. Let's see if we get a graph. So we get C goes to F and A goes to D and B goes to E, D goes to E, F goes to E. Great. We're able to construct our graph. Now, after we construct the graph, we need is to make a set of possible nodes to work on, starting with C, and pick the first alphabetical node and remove it and its edges. So we should also return all nodes. This is actually edges. So let's return nodes and edges. To get these nodes and these edges. And it's important because E is a node, but it's not a key in this dictionary ever. And likewise, C is a node, but there's no edge that ever points to C. So we want to identify both nodes that are parentless, meaning we can start work on them immediately, as well as the node that we end up with. We want to make sure we don't miss it. So we want a method to pop off the first node that doesn't need work, and we can keep calling this method afterwards. So So we want to find the next node to work. So what we need to do is we need to go over all nodes and see if any edges point to it. And if no node points to an edge, then that can be the edge to work. So possible nodes to work equals nodes or parent children in edges dot items if this child, like A is a child, is in the set of possible nodes to work, we know that it's dependent. Something is before it, so we need to remove it from possible nodes to work. Yeah, so we can call remove on a set. And we would loop over all the edges. We would do if possible nodes, or just return the first one alphabetically. Let's just sort the set. So let's try this. We will edges nodes equals we were able to find the first one, C. Great. So then we can remove C from the nodes and the edges, and then continue calling this function. So let's say we find the node to work, and while there are still more nodes to work, we will remove that. Nodes.remove, node to work, edges.remove, node to work. Print node to work. All right, so we get CABDFE. So what we're doing is we construct the graph first, so to get all the nodes in a set and the dictionary of edges, and then we work the nodes. So we have a work order string that we're going to print out at the end, and while there are still nodes to be worked on, we'll find the next node to work, which is the alphabetically sorted node that for all the nodes possible, so we make a copy of the nodes, and then for all the edges, if the child is in an edge, then we remove that as a possible node to work, and the nodes remaining are nodes that don't have parents, and so then we can return those, or the sorted one. And so then we will remove that work. We essentially work that node, remove it from the edges, remove it from the nodes, and then return the work order when we're done with all the nodes. So let's try it out. Our input, we get this work order. See if that's right. Yes, that's the right answer. So we got one gold star and we can do part two. Oh boy. So part two, as you're about to begin construction, four of the elves offer to help. The sun will set soon. If it'll work faster, it'll go faster if we work together. Now you need to account for multiple people working on steps simultaneously. If multiple steps are available, workers should still begin them in alphabetical order. Each step takes 60 seconds plus an amount corresponding to its letter. A equals 1, B equals 2, C equals 3, and so on. So step A takes 60 plus 1, 61 seconds, while step Z takes 60 plus 26 seconds. No time is required between steps. To simplify things for the example, however, suppose you'll only have help from one elf, total of 2 workers, and that each step takes 60 fewer seconds. So step A takes 1 second, step Z takes 26 seconds. Then using the same instructions as above, this is how each second would be spent. So second 0, we start on C, we work that until we get to second 3, where we can start on A and F together. And then in second 4, we're done with A, so we start on B, but we're still working F. And 5, work, work, work. We're done with B, then we start D, we're done with F, then we go through E. Then we finish at 15th second. So each row represents 1 second of time. The second column identifies how many seconds have passed as part of the beginning of that second. Each worker column shows the step that the worker is currently doing, or dot if they're idle. The done column is completed. All the steps has changed. This is because the steps now take time to finish, and multiple workers can begin multiple steps simultaneously. So now it's C, A, B, F, D, E, whereas before it was C, A, B, D, F, E. So it would take 15 seconds for 2 workers to complete these steps. With 5 workers and 60 plus second step durations described above, how long will it take to complete all of the steps? Okay, so in part 2, we still want to construct a graph. Now let's go back to our original smaller input. Now we want to do something like this. So So we still want to do while len nodes greater than 0. So we still want to solve all the nodes. And we can have a timer starting at 0. Then for each iteration, we can increment the timer by 1. Bad at spelling. So we're going to do this. We're going to try this. Something similar. Let's just try as if we had one worker. Let's try. Well, this might be tedious, but we could just make a mapping. So we want to map the lower values. So we'll make n workers, and for each iteration through this, we'll find node to work, the next node to work. But instead, we will find all nodes to work. So we'll take this, take it out, and here we'll simply return the first one. For each tick, we'll reduce the seconds left 1, less than 0, we'll reset it to 0. And self.current node equals none. And self.free is true. And we can also assign work to worker, so def assign node. So we will say self.current node equals node, and self.time, seconds left, equals the map of letter value node plus base time. Or we can assign base time as an initializer. Yeah, let's do that. So we will also say self.baseTime equals base. So add base time in the initializer. So we'll make worker with base time. So for worker in worker pool, if worker is free, then we will assign it worker assign node. And we'll tick for worker in worker pool worker.tick. So when we tick and we get done, we will return that. And if we get a node back, if finish node not equals is not none, then we will remove it. This way. Then we will let's print what the worker is working on in each second. So So C never finishes. We're in an infinite loop with C. So what is going on? We're always at 3 seconds left. So we always append that. We're always adding the node. So if node is not in if node is not nodes being currently track of nodes currently worked. When we finish a node, we'll remove it. Let's try that. So workers got 3 seconds left. We have an issue here. So let's see what's going on. So the first worker is working on C. After 1 second, there's 2 seconds left. And then after that, there's 1 second left. And then the worker is working on F with 5 seconds left. Happens. Then it works on F, and then nothing is worked on. But after C, A and F should have both been worked on. So why isn't F worked on? Or why isn't A worked on? So let's step through this. So we have our nodes. We have our nodes to work, which is C. So we can step to that. 3 seconds left. Should be 1 second left. No seconds left, right? So worker 1 is free. Our nodes to work is A and F. We have no words currently being worked, and both workers are free. So then what happens? Let's step through this. Right. So node is A, it's not currently being worked, and we're looking for a worker that is free. And so we're going to assign A to that worker. So let's look at our worker pool. So the first worker is getting A, and A is added to nodes currently being worked. So then the second worker is free, but node is not in nodes to be worked. Then we exit out of that for loop and going on to F. F is not in the nodes currently being worked. The first worker is free. So when it is assigned, we need to say free false. Self.free equals false. Stop and run it and see if that works. It took 15 seconds, which is correct. So let's see if what we can do with 5 workers, the full input, and 60 base seconds. Took 21 seconds. That cannot be right. Oh, we're stopping early. So total time is 891 seconds. Let's check that. Great. So we also got the second day. So like this videos, if you appreciated that, let me walk through this really quickly so you can understand what we did. So we made a worker pool, which is a list of workers, and each worker is an object that has the current node the worker is working on, the seconds left in its tasks, if it is free or not, and the base time that tasks take. And then when a worker is assigned a node, we're going to set that current node, set the seconds left to be the letter value of the node plus the base time, and say that the worker is no longer free. And then we're going to tick through this pool. And we're going to simulate seconds going by. So we're going to decrease the seconds left by 1. And if the seconds get down to 0, then we're going to say the node is finished. We're going to unassign the current node. We're going to set the worker to free, and we're set seconds left to 0. And we're going to turn that finished node. And so when we return a finished node, we remove that finished node from the list of nodes that we need to work. and we also remove it from the list of nodes we are currently working, and we remove it from the edges. And what is the set of nodes we are currently working? That is keeping track of what nodes are currently being worked, because when we find all nodes to work, we are still looking at the set of all possible nodes to work that haven't been done yet. So we don't want to add a node twice if a worker's already got it. So for the nodes that are possible to work, if a node is not currently being worked on, we search for a worker that's free. And if the worker is free and the node is not being worked, we will assign that worker and then add it to the nodes currently being worked. So that is how we're going to approach that. And so we keep doing that, and each time we hit the while loop, we tick through the workers and then remove it. And so then essentially we're simulating time going by. And then when all the nodes are done, we'll exit and we will return the time. So that's how we solved day 7. If you like this, please subscribe, and I will post the next video soon. And please support me on Patreon, because that really helps me make more videos. Thanks, and I'll see you later.